Welcome everybody. This is our session from Simutron, the reseller of the Altair simulation products in South Africa. A break free from meshing nightmares. Dive into Altair SimSolid's fast and efficient simulation solutions. Simutron is part of the MiCAD group of companies based with offices in Centurion, Durban, Cape Town. And Simutron has been a Altair channel partner since beginning of last year. Altair has been selling directly to South Africa, but they wanted to expand, so they looked for a reseller to assist with that growth. Excellent. So how does it work? The Altair licensing model, which is quite unique. It is called units. A license model that what it allows you to do is it's the analogy of a library. So in other words, what you do is you use the software tool that you need at the time. Because as we often know, for instance, you wouldn't be doing computational fluid dynamics, CFD simulations as often as you would do structural FEA type simulations. So you only use the tools you need as you need them. It's a leasing model, so year to year. And what's important is that it allows two options, either a hosted licensing, where it's hosted on the cloud, on the internet. So as long as you have an internet connection, you can work from any PC or any device. The software installs locally on the device, and then you're able to access the license by just logging in with your username and password. There is the other option, if there's high security reasons or you don't have an internet connection, you can host the license locally on your premises. So both options are available. Both options allow you to be checking out licenses. Maybe you're going to work in an area where there is no internet connection. Then, of course, you can check out units as you need them for a certain period of time. The other benefit is that we have a system known as leveling with the software on a user's machine. For example, which I'll be showing today, the product SimSolid, it utilizes a minimum of 30 units. Now, if you then needed to work with a product, say, for instance, HyperWorks, which would need a minimum of 21 units, when you open that product, it doesn't then try to take 51 units. It actually still only draws 30 units. So it's the concept known as leveling. If my colleague, however, wants to open it up, there has to be additional units available. Then it starts stacking, the concept of stacking. Great. And then in terms of how a user or company accesses their products, it's from the Altair One Marketplace website. And here you can see the various products, and it's almost it is the analogy of apps. So you download the software that you need, as I said, onto the device that you're using. You can see how you have SimSolid, SimSolid Advanced, SimSolid Basic. The Advanced giving you additional features in terms of fatigue analysis, etc. And as I said, as long as you have the unit count, you will be able to open the software and start your simulations. So this is just a quick just to show you an overview of how it works. As a company, you just go in, download the software you need. As we said, as if you're accessing from a library, use the product you need, and then the units will just go back into the pool after you've completed your work. So it's a very flexible licensing system. Right. What we're talking today is about SimSolid. Is a structural simulation that operates directly on original unsimplified CAD geometry and does not create a mesh. As we know, those are two key important points that typical finite element analysis processes involve tremendously tedious pre-processing in terms of simplifying geometry and creating the mesh. And then the other benefit with SimSolid is results in seconds to minutes, even with large assemblies. And we're talking large assemblies, 3,000 parts plus. And then the key word as well is simulation at the speed of design. I'll highlight this more. The idea being that the idea of SimSolid is it's CAD agnostic, meaning it can bring in any CAD format from any of your CAD vendors. And as you're working through your design, you start using the SimSolid tool to simulate as you're working. So it doesn't become the process or typical process of completing the design, then doing the tedious work of the simulation, and then going back and making a design change. This allows you to do that in a much more efficient, high-speed fashion because you're circumventing the two big key pre-processing operations. Again, as we are highlighting here, SimSolid eliminates the two most time-consuming and expertise-intensive tasks of traditional simulation: geometry simplification and meshing. And this is a key word, expertise-intensive, which is very true. In terms of geometry simplification, how do you know how much you can simplify the geometry? To what extent? Can you remove bolts where there are bolts? Can you remove the welds where there are welds? And that requires expertise and, of course, extensive knowledge of the product. And then as well as meshing, where do you have a refined mesh? Where's global, a larger element size acceptable? So SimSolid, you just avoid those two issues completely. So in terms of geometry simplification, let me highlight again, we're talking about you do not remove part. You can, so you bring in a full assembly with nuts, bolts, washers, springs, all parts in the assembly. You do not need to worry about removing anything. You do, however, have the choice, of course, in SimSolid. If there are features you don't want to include in the simulation, you can either delete or suppress them, and they will not be included in the simulation. So that's not a problem. So the meshing roadblocks, as we know, assemblies with big and small, or thick and thin parts, as we know, that can be tremendously challenging in typical FEA workflows in terms of trying to interface. For instance, if you have a shell element, a 2D shell element mesh connected to a 3D brick mesh, how do you interface and connect those? Because they have different degrees of freedom. So it often can be very challenging and time consuming. Here you can see an example, small geometry features. You've got thick components, thick walled sections with thin walled sections, and many holes and small bosses, and all difficult features to mesh. And the problem is, can you exclude those because of potential stress concentrations? And then part gaps and overlaps, of course, very critical for contact. Can that be excluded or included? It has to be considered. And then as well, this is an example, of course, of a 3D printed part, and we are going to get there in the future. But the point being that this product allows you to be solving very complex parts with arbitrary shapes. And then the other part is the face transitions or small splinter surfaces that you may need to deal with. So as we're saying here, this is all handled inherently with SimSolid. So, and the typical workflow, you've got simulation effort versus geometry complexity, parts and connection. You can see how the classical FEM is an exponential function. SimSolid allows you can see it as a lower linear effort in terms of setting up the model, because of the fact that you don't have to defeature and remove or clean up geometry, and you do not have to mesh. SimSolid is large model capable. Here you can see a part that was analyzed within a minute or two with over 2,000 parts. So it inherently does this very simply, and this is a dynamic analysis, a modal analysis, which can take which will take longer than a linear static simulation. A product fit, early simulation driven design, and this is our keyword in the fact of where this product is well placed. As I said, it's very much designed to be upfront in your design process. As you're designing and doing your 3D CAD modeling, you can be assessing your assemblies with SimSolid. As I said, it's CAD agnostic. You can import any CAD format from any CAD software, and you're able to analyze and assess. And if there's design changes, you just import new parts and continue to work. Just a note, SimSolid does not have internal CAD editing tools, so you cannot work on the CAD inside SimSolid. But that's not an issue because it allows you to remove and import parts from your CAD software. Because again, as we know with FEM tools, CAD software is always has more power than a CAE tool in terms of CAD modeling. So just a note on that. And so here you can see how the benefit is the design iterations upfront, allowing a shorter time to validation and a quicker output to the finished product. Now, just another note, SimSolid is not designed to replace traditional finite element analysis. I will show a simple case study from a customer of Altair's that they use the tool upfront in design and then use simulation FEA tools afterwards. So it's very much, as you said, a tool that can be used upfront, should be used upfront in the design process, as well as it can be used for high fidelity simulation work, but it's very well placed to work in the beginning of your design process. So just an overview of the customer and references. Renault, Jaguar, you can see most of the high-end automobile industry, Fortune 100 and 500 companies, and other heavy industries from all over the world. Altair is actually based in Detroit in the US, so they work very closely with the motor industry, the automobile industry. And what's good here is a case study that, because as you know, and I'll get to that later, verification of the software in terms of how it's solving and assessing and how accurately is it calculating results is one thing. But what is it doing in real world scenarios? And that's very important. And here you can see where they assessed chassis components and they were able to achieve accuracy, the worst being 10% error, with a lead time reduction of conservatively 25 times faster. So it was, as they said, commented here, no expertise in analysis is necessary, especially no meshing is required. Also, SimSolid helps our designer to shape chassis components with confidence based on the SimSolid simulation. So you can see here as an example with this bar chart of the input, run, output, and the total benefit. So as I said, they're using this upfront, and we can happily share the story that's available here. So just an overview, SimSolid simulation capabilities, solutions, modal, linear static, nonlinear static, frequency, linear, transient, random response. So that is all the dynamic types of simulations you'd need to do. Thermal and thermal stress, inertial relief, bolt pretension, linear superposition, as well as the option of fatigue assessment, linearized stress if you're working with pressure vessels or particular API codes, incremental loading, incremental nonlinear. It covers the full spectrum of simulations, and the Altair team is working extensively on increasing the functionality of SimSolid. Materials, isotropic, elastoplastic, rigid, fluid bodies, orthotropic, user input SN-EN curves in terms of your fatigue assessments, your stress life or strain life curves. Just a note, the software does not cater for a large deformation in terms of 400% plus in strain. So typically that would be high deformation of rubber or hyperelastic materials at this moment in time. The connections, auto connections, as you bring it apart, it prompts you to apply your connections. By default, that is bonded connections, and you can then change it to either sliding and then separation with friction, which of course is then a non-linear type contact. So a non-linear analysis must be conducted. Bolts catered for, as I said, because their bolts are in the assembly and you leave them in the assembly, you use them in the analysis. It's not the typical workflow of FEA where you'd remove those bolts or use them as a guideline to apply your 1D, or if you have the computational resources, you'd model it 3D, but again, with a lot of effort. Spot welds, solid seam welds, stitch welds, bushings, rivets, virtual connections, adhesive joints, because again, as we've said, Altair works closely with the automobile and aerospace industry. Results, contour plots, animations, your typical displacement, stresses and strains, frequency, modal shapes, modal participation factors, critical in your dynamic assessments in terms of how much of a percentage of the mass is acting for a particular frequency, safety factors, contact forces, and total strain energy. So here you can see just some examples, linear static, and this is the pull-up bar example I'll be showing just now. Contact, you have, nonlinear static, contact, material, geometric, bolts, pre-tension. Here you can see in quite a different fashion what SimSolid does is when you input the pitch of the thread, it asks you to input the number of turns on the nut, and this will of course then generate the appropriate preload in that bolt. And then inertial relief, which is important when you've got conditions where you don't know the boundary conditions. For instance, an object in space or air, or a vessel on the sea, for example. Here you can see also a thermal analysis example. This is a simple example of a toaster where they are plotting against across the top of this the temperatures. So as you can see, you can extract all the information that you want to, and as you work, you can save and export the information as CSV files. Because as we know that we still need to report on the results, which is quite a tedious function, but I'll show just now in the demonstration that SimSolid helps you in this regard. SimSolid Solutions, modal analysis. Here you can see a complex structure with many parts conducting the modal analysis. A simple part here for frequency response, a tuning fork. Here you can see the response based with different damping ratios. A transient analysis where you've got a short and a longer beam and what the response is of those. And as you can see, these are single parts here, for example, no meshing, importing the parts, setting the analysis up and running. And I'll show that just now. And then random response, you've got your input PSD and then your response, of course, for other machinery type equipment where it doesn't have a known input force. Again, the SimSolid connections, auto connections, as you bring in your geometry, it asks you with what tolerance and gap you would like to connect your parts together. It picks up automatically the different distances that are in the part. So as it's importing, it assesses the part. That is the same in terms of identifying, as I said before, what is a bolt. So how it does that is it picks up any shape, anything that is any part, that is a hexagonal shape. It will then apply the part type to be bolt or nut, whatever the case may be, and then that then allows you to identify the specific areas. And what I'll show as well, the software goes a step further. You can imagine that where that bolt shank goes through the part, you would then have sliding contact, because as you know, that would not be bonded contact because the part is touching inside there. So it will automatically apply to where the shank interfaces with the part a sliding contact. And again, as I said, I'll show that just now. Here you've got an example of spot welds. And then, of course, a very commonly used function would be applying seam welds. And this, of course, would be instead of applying global contacts. Of course, you have the option of using both together as well, but under certain conditions, a fabricated structure, it would be most suitable to model that with welds. And then again, the concept of, in this example, virtual connections, which is almost the analogy in typical finite element analysis of multi-point constraints, MPCs. So where you're able to replace parts, but apply a particular condition to induce that behavior. So here you can see it's a hinge that allows that part to then swing, similar to a pendulum. And here you can see an overview of SimSolid results contours and animations available on the fly as you work, displacements and stresses. Here you can see frequency and mode shapes. And of course, as anywhere for any of the results, you can output XY plots, which, as I said, can be exported to CSVs. Further to that, as I mentioned, modal participation factors, very important when assessing your natural frequency results. How much of the mass is acting in a particular direction for a particular frequency. This can help you in terms of how to counteract that particular natural frequency if, for instance, it's too close to a operating frequency. The extraction of reaction, contact, bolts, weld forces. So very important for welds, you can extract your shear forces, normal forces, bending forces, and bending stresses from the welds. Very important for weld design. Of course, min and maximum labels, where's your maximum result. Safety factors, important when conducting linear analysis. Just a note on SimSolid documentation. As we know, it's very important with all CAE software for it to be verified. So Altair, when it releases software, has more than 35 problems explained where it will run these problems before each release of the software. As well as that, you may have heard of the non-profit organization body called NAFEMS. All CAE vendors in the world use a battery of problems defined by NAFEMS, and these they use to help verify and validate their solvers. So again, SimSolid not only uses Altair's examples, they use NAFEMS examples, and then as well as a real-world validation manual that is provided for SimSolid, and then of course, very important, customer stories in terms of real-world examples that have been solved, comparing SimSolid to other finite element analysis tools. So important in terms of technology overview. How does this technology actually work? SimSolid computational engine is based on breakthrough extensions to the theory of external approximations. External approximations are generalization of the finite element methods in terms that absolute arbitrary geometry shapes can be defined as finite elements. So let's just pause for a moment. Single parts as well as multiple assemblies can be imported into SimSolid. Each of those parts is defined as an element. So no matter what that shape of that part is, it is an element. Important to note, SimSolid only works with volumes. Very important to note. Whether they're thick or thin, that's not the problem, but you can't import 2D surface that does not have any thickness or any curves. It will ignore that type of geometry. So it only works with solid geometry. That is how this method is developed. Basis functions which approximate field of interest in the part volume can be arbitrary class and are independent of the volume shape. Now what that means is holes, radii, certain stress concentrations are catered for with basis functions in the part volume as stated, independent of the shape. So SimSolid Solver is not worried about the shape. It's solving for the features within the volume, as I said, which is a finite element. So SimSolid does not use the point-wise degrees of freedom inherent in traditional FEA. In other words, it does not define nodes. SimSolid DOF's degrees of freedom functionals with geometry support in the form of volumes and clouds. This provides the ability to handle geometric imperfections as well as assembly contact imperfections. Again, as I said, it can cater for gaps, penetrations, and very ragged contact areas, quite intrinsically. SimSolid controls solution accuracy using the multi-pass adaptive analysis. So because what you need to do, and I'll show that now, is you have to solve for the approximate error at the boundary conditions. So the technology steps in terms of modeling, how does it work? When you import the geometry, the process, it converts it to faceted volumes. It classifies the geometry internally, as I said, identifying bolts, nuts, washers, springs, thin sheets, through holes, etc. Create connections that then asks you and prompts you in terms of defining contact regions between parts found automatically, or to specify contact condition, bonding, sliding. And as I said, if there are bolts, it will automatically define where there's sliding between the interfaces of the bolt and the part. User specify contact condition, separating. That, as I said, is a non-linear type simulation where you've got separating of the parts. And then finally, the user create analysis parameters, analysis type, boundary conditions, material properties if not inherited from CAD, because SimSolid does have an interface from certain CAD software that allow it to import directly from the CAD, and it will bring in the material properties. Solution adaptation control in terms of the accuracy levels you're looking for, which again will increase the solution time. So it's very much dependent on what level of solution or answer you're looking for. And then in terms of SimSolid's unique adaptive solver technology. So again, as I said, part and feature recognition evaluation, create initial equations, solve equations, extract strain stress, error analysis, check the displacement errors at the constraints, the traction force errors or free surfaces of parts, displacements and energy convergence analysis. If this is not achieved, then degrees of freedom and all those functions are added locally at the constraints and connections, or in the volumes, as I said, around certain features like holes, radii, etc. And then it is rerun, and the error analysis is checked again to be within a certain tolerance. And if not acceptable, again, it is added, degrees of freedom are added if you allowed for that many loops and repeat based on specified number of maximum passes. So the software by default runs 3 passes by default. You can increase those number of passes to check for convergence. But the software comes with certain guidelines. So it's not a matter where the user has to spend their time worrying about what will be an accurate result. There are specific guidelines, and of course, Simutron is available to assist you in your process when you decide to have a trial of the software and also purchase the software. So what is the steps when doing the extraction of results? This is important. Create response mesh used to map results to design geometry can be redefined on the fly. So you can see the results have been mapped to the various features here, the radii, the holes, values determined at nodes, but that's obviously pseudo nodes of the mesh. And again, it's not a mesh defined by the user, it's a mesh defined internally by the software. Display reactions that supports connections, parts, resultants. Fast reanalysis. SimSolid remembers response, mesh, and incremental analytical functions. So reanalysis typically processes quicker. So it's all live in the RAM, solved on the fly. The software, because of its the solver technology, does not require high-level computational setup. We've run problems very successfully with standard even 4-core, 8-core, 16-core machines with as low as 2 gig of RAM. It's really very efficient in terms of memory output. Of course, the larger the assembly becomes, the more computationally intensive it is, but we haven't found a problem that we haven't been able to solve up to this point. And that's, as I said, easily with plus 3,000, 6,000 parts. As mentioned before, verification manual, of course, important to define simple problems that have been verified against either experimental results or other finite element results. Here you can see a particular case where SimSolid was compared against OptiStruct. OptiStruct is the Nastran solver from Altair, Nastran derived, solver from Altair. And here you can see 70 part assembly, 1.1 million second order tetrahedral elements used for this mesh. So a full solid mesh for this structural analysis of the chassis. And here you can see the modal frequencies correlating very closely. SimSolid mapped the displacements of both the FEA and the SimSolid, and here you can see 6 solution passes and then adapted to thin solids because of the thin walled parts, because that typically you would be modeling with shells in a finite element mesh, for example, if you so wanted to set that up. Major principal stresses, outputs, as you can see, similar results. And then in terms of, again, a case of an engine, 700,000 second order TETs, bonded connections. Here's the natural frequencies compared with OptiStruct, also close correlation. With it hasn't been quoted here, but the benefit being that the solution times are dramatically less than the finite element model equivalent. Modal analysis of a golf club driver, and here you can see, this would be very complex to do a finite element mesh. Here you can see how you've got thicker sections transitioning to thinner sections, so typically you'll use full 3D solid elements, but of course you're going to have a massively large count of elements, or you mix it with 3D and 2D shell elements. And here you can see for mode 7, the natural frequencies, 2020 for SimSolid, 2054 for OptiStruct. And here you can see the comparison, with the worst being 1.3%. Here you can see an example of a piston assembly, natural frequencies, and including your bolt contact. And here you can see the effort in terms of setting up that simulation. So SimSolid saves you tremendous amounts of time in model setup, as well as solution and post-processing. Here we have a grapple hook. Here you can see modulus of elasticity, Poisson's ratio, your density, load, constraints, where it's fixed. And we have both SimSolid and OptiStruct. And here you can see excellent correlation in terms of a particular stress concentration, as well as your displacements. Excellent correlation in terms of eigenvalues, your natural frequencies. And then a B pillar static analysis. Here you can see as well with SimSolid and OptiStruct simulations with great correlation. Here you can see the displacements and stresses and the actual contour. A powertrain head and block, so that's with a crankshaft and the connecting rod and the pistons. Elastic modes comparison. Here you can see correlation, the worst being nearly 7.7%. So, typically we're looking for 10 to 15% error. So, as you can see, it really gives good, strong results, and the benefit being in a very short amount of time for the entire process of pre-processing, solving, and post-processing. And here you can see a complex model in terms of trying to calculate the Hertzian contact pressures. So this is a non-linear contact analysis, 2 parts. And again, there you can see SimSolid and OptiStruct validations with the output, the contour plot of the displacements showing excellent correlation. And you can see the output reaction forces for 0.1 millimeter of deformation.